So hi everyone. Today we have Sabina with us. She's doing her PhD in quantum physics at ETH, and she's also working in IBM Zurich. And today she's going to tell us about quantum algorithms. So I'll leave the floor to her. Thank you for coming.
Cool. Thank you for inviting me and for having me. My name is Sabina. As Mar just introduced me, I'm a PhD student in the physics department at ETH and also work with IBM Quantum. And today I'm going to talk about quantum algorithms. I'm going to start from the very basics of what a quantum computer is and how it works, and then the theory of how to solve problems using these quantum computers, and finally try to look at how to actually implement them on real hardware. So today's talk is going to be about this mysterious thing that people introduced only last year called quantum utility. And the goal is going to be to try to explain what it is and if we're actually there. And in order to answer that question, we're going to have to go straight to the basics of what the actual computer is. We're going to look at specific problems and certain algorithms that we use to solve them. And finally, we're going to look at error mitigation techniques. Because the hardware is still noisy, we need to process the results that we get from the quantum hardware. And oftentimes, this requires us to go back to the original problem to create custom-made techniques for error mitigation. So if you're going to get anything from this talk, I want you to get that the pipeline of solving problems on quantum computers is not linear as what one might expect, but rather it's an ecosystem that you need to take care of in its entirety. So let's start with some motivation. We're going to look at what kind of problems we can solve with quantum computers. And we're going to start with quantum systems. Quantum computers were actually famously proposed as an idea for solving these problems by Feynman because it's such a natural application. And I'm going to go into the details of why it's so natural a bit later. A less natural application would be optimization problems that we are, if you're into CS or math, you're very familiar with. They're like discrete optimization problems on graphs, or financial optimization, or Monte Carlo-like applications. And what these two applications have in common is that you can encode the solution to them in the ground state of a Hamiltonian operator. That means that we want to solve this equation for those that don't have a physics background. And the simulating quantum system problem is exactly just this problem, finding the ground state of this Hamiltonian, which kind of explains why quantum computers are such a natural platform for these problems. But for optimization problems, because they are classical, we are going to have to go through an additional step of mapping them onto onto the Hamiltonian. So why are these problems hard to solve? Without going too much into the detail, the idea is that the solution space scales exponentially with the system size. So you cannot brute force it. You can come up with smart ways of going around it, and there are definitely approximating algorithms that try to do it, but it is still a challenge for classical computers. And similarly for combinatorial optimization problems, if you are familiar with like the traveling salesman problem, all of these are NP-hard problems. And some of them, even approximating algorithms, are NP-hard. All right. So that's kind of the target that we want to solve, the kind of problems that we want to solve. And now, for those of you that don't have a physics background, I wanted to talk a bit about the basics of quantum computers. And I think the easiest way of introducing the motivation for a quantum computer is to go back to the classical way we encode information, which is with bits. That can be 0 or 1. And now qubits, we're going to say they can be either -1 or 1. But if this were just it, then it wouldn't really make sense to look at quantum computers in the first place. So the additional perk they have is that their states are not just -1 or 1, but it's a vector psi on the unit sphere. So instead of just -1 or 1, it's a probability distribution of these two values. And we can, in this way, encode two pieces of information with just one. Now, another important block of quantum computers are measurements. So even though the state of the qubit is a vector on the unit sphere, measurement collapses this. So when we look at the qubit, we are going to see either -1 or 1. And this is how we see this surjective mapping between the classical bit and quantum bit. So for example, if you have 3 qubits that are in an equal superposition, which means that we only have this uniform distribution over all possible basis states. So the basis states are the 3-bit long bit strings. And yes, this is the state. And we have this state, and when we look at it, it basically collapses to something like this. So up, up, down. And this is how we get only one of these measurements. So to actually get this entire probability distribution, you need to make a lot of measurements. In this case, I made 10,000 measurements. So this is going to be important, the fact that we're going to have to make a lot of measurements to actually extract all this information, the probability distributions, instead of just the basis states. And from here, I want to leave you with a bit of a taste of why quantum computers might have some sort of advantage. So suppose you have a problem whose solution is going to be the bit string 001. And you start with the uniform distribution. And what you do is you apply a quantum algorithm that for now we're going to leave an abstract thing, which is just a sequence of gates that you apply. And what those gates do is that it amplifies the probability that you're going to end up in your solution state. So you have this relatively small number of gates in your algorithm that put your state in this superposition. And then when you measure, you're going to have a very high probability that you end up in your solution bit string. Also, feel free to ask questions and interrupt me if there's anything unclear. Okay. So we kind of talked abstractly about what a quantum computer is, but I also want to give you a bit more physical intuition. And particularly, I'm going to talk about the different architectures that are out there. So because the main goal of my talk is to go from theory to hardware, I also really care about the hardware. And what all of these hardwares have in common is that they have qubits. And all of these qubits have many energy levels. So a qubit is kind of an abstract concept that we defined as the quantum analogous of a classical bit. But physically, it's a physical object, like an atom or a circuit. And what these atoms or circuits have in common is that they have these many energy levels, but we only care about 2, the 0 and the 1. And the way we go to a 0 or a 1 is by applying laser pulses, which are very finely tuned. And if your laser is not very perfectly tuned, then you're going to be introducing errors into your algorithm. The point of being that the controls in these computers are very sensitive and very prone to errors, more so than classical computers. So the qubits I was talking about, all architectures have them, but there's different types of architectures. And I'm not going to talk about all of them. These are just some of the more established examples. So you can have qubits being neutral atoms, or ions, or superconducting circuits. And I want to draw some comparisons between the architectures that are out there. And I want to start with what I care about, and I'm going to explain later why I care about this. But it's about connectivity. So neutral atoms have a pretty good connectivity, meaning that locally it's fully connected. So each node is fully connected to a lot of its neighbors. Ion traps have very good connectivity. You have a very fully connected graph where each node is one of the qubits. And superconducting qubits are not so good. they have what they call the heavy hex topology, and it looks kind of like this. And basically, each node is connected to its nearest neighbors, either 2 or 3 neighbors. However, another important thing for computers is that you're able to control each of these qubits. So the fact that this topology is more sparse allows you to better control each individual qubit that you might want to do for certain problems. Ion traps also have this addressability, but neutral atoms not so much. And really, what we care about in the end is going to be to have a quantum computer that solves your problem faster than a classical one, not maybe just through the fact that you have an algorithm, but also through the actual computing times. And here is where superconducting qubits have a very strong advantage. The conclusion of this comparison being that we don't really know which architecture is best, but you should be aware that there's many of them. And when you read about news, in the news about progress made in quantum computers, it's also really important to see what kind of hardware they used. But for the rest of the talk, I'm going to talk about superconducting qubits because that's the kind I've worked with, yes.
Are all of these differences stuff that we put in the constant in computational complexity, or do they make a difference in the computational complexity of the algorithms as well?
They definitely play an important factor in the complexity, and I'm going to talk about that later. This is why I wanted to kind of draw attention to the connectivity, because depending on which connectivity you have, the factor is going to change dramatically. Okay, so we kind of know what problems we want to solve. We kind of know what the computer is. Now let's kind of dive into more specifics. So I'm going to start with giving kind of a general recipe for implementing a quantum algorithm, implementing a problem on a quantum computer. And the first step would be to map, if your problem is classical, to map it onto a quantum. And we mentioned before that we don't really have to do this for simulating quantum systems because they're already quantum, but we are going to have to do it for optimization problems. Second step would be to pick your favorite algorithm, and which I mentioned a bit earlier. It's basically a sequence of predetermined gates that you apply in a circuit, and then map it onto the hardware, which is going to look like that. And finally, because the hardware is noisy, we're going to want to error mitigate the results that we get from the hardware. So I'm going to go into the details of how to do each of these steps. This is just an outline. All right, so let's start with how to map a classical problem onto quantum hardware. And I'm going to talk about max cut. I think this is one of the most talked about problems, or the one that the most experiments were done for in the literature. And the problem is as follows. You have a graph, sigma, with a set of edges, E, and a set of vertices, V, and you want to split it into two subgraphs such that the sum of the edges connecting the two subgraphs is maximal. So in this case, one of the subgraphs is going to be with the black dots and the other one with the white dots. And we're going to assign each node a binary variable, 0 or 1, depending whether it's, let's say, in the first subgraph. And the way you encode this problem classically is trying to find the argmax of this sum, where the sigma ij is just the weight of the respective edge, and the product xi times 1 minus xj is going to be 1 for pairs of nodes in different subgraphs. So you can kind of see that this function is really looking to maximize the number of such pairs in different subgraphs. And to map onto quantum hardware, we basically want to map onto the Hamiltonian problem. And the way we do this is by replacing the binary variable xi with the eigenvalue of this operator y minus zi over 2, where zi is the polygate with eigenvalues minus 1 or 1. So when I say polygate, it means it's an operator that we can apply on the actual quantum hardware, the same way one could apply a XOR gate or NOT gate on a classical computer. And then just plugging in xi with this value in the expression above, we can map the argmax problem onto an argmin problem. And without going much into the mathematical details, this basically means that we want to find the ground state of this encoding Hamiltonian. So, okay, now we have our mapping from quantum solution. Like if we were to solve the ground state energy of this Hamiltonian, we would have a quantum solution. And we know how to go back to retrieve the classical solution to the original problem. But we are still left with the question of how do we actually find this ground state. And so next, you pick your favorite algorithm. Here I kind of picked a random, not so random algorithm. It's not so random because it represents a bigger class of algorithms known as variational algorithms. But there are also other algorithms you could use to solve this problem. So we have our Hamiltonian H, and the way you would implement it on hardware is by time evolving it, meaning that you encode this time evolution operator onto a set of gates. Okay, and as you can see, or if you're familiar with the Schrodinger equation, what you would get is e to the minus it zi zj, but you also have this additional parameter gamma, and that is the variational parameter that gives the name of the algorithm. So what you do is you create this ansatz, so this circuit, which has a predetermined set of gates, but each gate can take in a parameter. And you run this algorithm, this circuit, and at the end you perform measurements, and you extract your probability distribution. And from the probability distribution, you can compute the energy corresponding to that state. And then you use a CPU, so a classical side, to perform a gradient descent step and adjust the parameters. And then you feed it in the new parameters in your circuit, and you iterate over this loop until your minimization algorithm converges. Cool. So, yes?
So at the end, this is going to give us a probability distribution over the space of all possible solutions?
It's going to give you a probability distribution over basis states, which when put together gives you a state. And each state has a corresponding energy. And then you compute that energy, and that is the parameter that you're really trying to minimize.
Yeah, no, I mean the whole algorithm. Like,
yeah.
They will get like a probability distribution over this like 0, 1 vectors that represent the partition.
Yes, it's a probability distribution over basis states. Cool. So this kind of works out nicely in theory. I see confused faces. If there's questions, please ask questions. Okay, so this is kind of the theory part, and if there were no errors, then we would pretty much be done with our problem. But it is now time to talk about the errors. So before going back to the original circuit, I just want to give a high level overview of where errors might occur. So the answer is pretty much everywhere. They can occur on single qubit gates because of the maybe misaligned laser or not so finely tuned laser. They can also occur on qubits like this last one that are not really doing anything. It's just the fact that they're in an excited state and they decay with a certain probability. But they can also occur at the readout. So when we perform the actual measurement, maybe the state was a 0, but we saw a 1. And each of these errors or types of errors occurs with a different probability. Single qubit gates have the highest fidelity. It's very close to 1. But then for 2 qubit gates, the fidelity decreases by like an order of magnitude, or the error increases by an order of magnitude. And the readout is even worse. And while these numbers might be very close to 1, if you're thinking about solving a very high problem with like 100 qubits and you have tens of thousands of these gates, then this is really going to affect your result. Now, for the problem you want to solve, we're going to have to do a readout at the end for each of the qubit anyway, so there's not much we can do about that. But what we can do is trying to minimize the number of 2-qubit gates. So this is not yet error mitigation or correction, but it's more trying to avoid errors altogether. And this is where it might be interesting for people that are doing math. And let me explain why. So let's go back to our algorithm. We have this time evolution and the ansatz, or the predetermined set of gates that we want to apply. And in this example, the ZZ gates only occur on neighboring qubits. And that's kind of a nice scenario. But imagine you want to implement the time evolution of a Hamiltonian from this graph, where you have ZZ gates between qubits 0 and 2 or 0 and 4. So abstractly, we would represent ZZ gates like this. It's just like connections between their respective qubits. But for example, if you want to apply this gate on the current hardware, then it's going to be a bit more difficult. So this is the hardware that we're working on. It has 128 qubits. And the rule of thumb is that basically the darker the dot, the higher the fidelity. So these white spots are not really well connected. But thankfully, this is a large device, and we can safely just pick a line of the best 5 qubits. Let's say this one. And then what we want to do is apply this ZZ gate on the two ends of the line. So what you have to do is, because you can only apply gates between neighboring qubits, you have to move the qubit on the left side all the way to the right. And the way you do this is by applying swap gates between each pair of neighboring qubits. So you have first to do a swap gate between those two, and then those two, and then those two, until the very end. So the circuit would look something like this.
So swap gates just like swap two qubits, right?
Yes. Yes, as the name says, swap gates means that you just swap two qubits. So here you're basically moving this qubit all the way to the last one. And in this case, it's not such a bad overhead to have. But again, if you're looking at larger problems, it can drastically affect the constant factors that we were talking about before. So what you can do is try to optimize over the initial ordering of qubits and the ordering of gates. So for example, if you were to have a gate between qubits 0 and 3 and 0 and 4, you could try to apply those gates one after the other to sort of overlap this swap overhead. And this is where the math part comes in. The way you would do this is try to find an embedding of the original set of gates onto an optimal ordering. If there's a question about this, I can talk about it later. So yes.
Is that optimization problem simple? Is it like, can we do it in polynomial time in general? Like to find the optimal ordering? Set of like gates between?
No, it's only an approximating algorithm, and it depends very much on the Hamiltonian you want to apply. So here we're only working with 2-qubit gates, but if you were to have higher order gates, or like gates that involve more qubits, then the problem would become a lot harder. So that was kind of trying to avoid errors, but the more established way of dealing with errors are error correction and error mitigation, which often appear in news because it's a very important area of research, but there's an important distinction that I want to point out. And error correction means that you're dealing with logical or encoded qubits, kind of like in the repetition code, where you use 3 classical bits to encode only 1, thinking that if there's an error occurring on one of them, you have a majority vote at the end. And doing this would basically require you to use more qubits, but the error correction would be done as you do the calculation. So at the end of the circuit, you know your result is not noisy. But error mitigation is fundamentally different. You're not working with logical qubits, you're still working with your physical qubits, so there's no qubit overhead. However, at the end, your results are still going to be noisy, and what error mitigation basically means is a smart way of combining these noisy results to get something sensible at the end. And this is exactly what this table shows, that error correction has a large qubit overhead, but no sampling overhead, and error mitigation has no qubit overhead, but large sampling overhead. And by sampling, I mean how many times you have to repeat your experiment at the end. However, current hardware is not only noisy, but also kind of limited in size, so we cannot really afford to do error correction yet. So what we're going to focus on is error mitigation. And I'm going to talk about two error mitigation techniques that are fairly recent, and which I like because they surprisingly work. So first one is called probabilistic error cancellation. And this is a circuit where the gates that we would want to apply are these blocks U1, U2, UL. But then we also model the noise that occurs as a channel or just another operator in front of these U operators. And what we would want to do is learn the noise. This is for the CS people in the audience. This is also not an easy problem to solve because you need a good intuition about what kind of errors can occur in your system. So you need to be able to model your errors kind of precisely. And the errors can also change. They're very volatile with time. So you need a machine learning algorithm that learns your noise in a short enough amount of time so that when you want to cancel it again, the noise is going to stay approximately the same. So, okay, assuming this machine learning part, or learning the noise, works out fine, what you would want to do is apply this lambda to the -1 in front of it to cancel the noise. But sadly, doing this operation is not exactly a physical way of doing it. So what people propose instead to do is decompose the channel lambda to the -1 into smaller gates, identity X, Y, or Z, and in short, basically, randomly introduce errors into your circuit so that it cancels out. Which I thought it's surprising at first because you're introducing more noise into your system, but there is actually performance guarantees for the final result that you can get. But sadly, it also comes with a sampling overhead at the end. Because the more errors you introduce, the noisier your result, the more samples you need to extract something useful. Yeah.
So the noise in this case is really not like the classical Gaussian noise we have in statistics. It's more something that is a lot more predictable what's going to happen.
There is many types of noise. I think the easiest way to model noise is just random X, Y, Z gates appearing in your circuit. A more physical type of noise is called the thermal noise, and that one is modeled kind of as a Gaussian distribution, the probability of the qubit decaying.
Yeah. So the noise has like two components. One, we cannot really do anything about it because it's just random, and one is that we can predict.
I mean, you cannot really predict how it happens, which is why you're going for this random application of noise, because I'm sorry, I might have missed this part, but if you apply an XX gate, then that's going to be just the identity. So if you have a random X gate appearing, you're going to apply an X gate with a certain probability, and that one is going to cancel out.
Yeah, but then in that case, I mean, at least mathematically speaking, it's like 50-50 if it's correct or not, kind of, right? Because it may or may not have
Yeah, pretty much. The probabilities are small of these errors occurring, but again, as you're looking at larger system, it can affect your results. So if you thought it's weird to introduce random gates to cancel noise, this is going to be even weirder. It's called probabilistic error amplification. So we're going to have the same setup, the gates U that we want to apply, and the noise lambdas. But now instead of trying to apply lambda to the -1, we're going to add noise. So you cannot really erase noise. As we were saying before, it's hard to apply lambda to the -1, but you can always introduce noise. And the idea of this is that you define a noise amplification factor and basically apply or add noise proportional to that factor until you get a curve that will let you extrapolate to the so-called zero noise expectation value. So that's the value that you would probably get if there were no noise in your circuit. Now, mathematical questions would be, how do you define this amplification factor? How rigorous this is? There's different ways of defining the factor. How rigorous it is not. It's a very heuristical method, but it's also very new. It's from like a year ago. So if you're interested or this sounds interesting to you, I would really like a performance guarantee for this. But the nice thing about it is that it has no sampling overhead. So you are going to have to basically redo the circuit for different such factors, but it's not going to be exponentially many samples that you need to take. Cool. So I think we're kind of ready to talk about quantum utility. I think I have it up a bit much because the conclusion is not going to be as exactly what you would probably want. So what is quantum utility? You might have heard in like the past 5 years or so about a paper put out by Google talking about quantum supremacy, or later after that, quantum advantage. And those really meant that quantum computers are better at certain tasks than classical computers. And quantum utility is something a bit more modest. It basically says that quantum computers can be useful in regimes where even classical computers have difficulties. And yes, this paper came out. It was a pretty big news. It was put out by IBM last June. And I'm not going to go into the details of this graph because there's a lot of background knowledge. But what I want to point out is that, first of all, the lines here, the pink one and the red one, are done with classical approximation methods that maybe some of you are familiar with, called MPS and tensor networks. And the mitigated hardware results are the blue dots. And the main takeaway from here is that they're kind of in the same ballpark, and that all of them are approximating methods. So we don't actually know what the curve is, but we're guessing somewhere here. And this was kind of cool, but people didn't really think so, because 2 weeks later, they put out another, obviously not the IBM team, but someone else put out this paper saying, hey, we came up with a better approximating algorithm for this specific problem. And of course, that doesn't really paint a nice picture of quantum algorithms, but I personally also don't really think that the goal would be to have this quantum algorithm that's always better than the classical one. It guarantees that you have a pipeline, or like this quantum algorithm that solves a problem approximately well. So you don't have to go through coming up with like a smart classical way of simulating it every time you have a new problem. It's just going to be kind of automatic. And so the main takeaway from here is that quantum utility, quantum advantage, supremacy are all kind of ambiguous and in continuous development. And I don't know if we're there. There's probably a long way to go there. But I think these problems that they pose are interesting. And the conclusion for today would be that successfully implementing quantum algorithms is difficult, which I don't know if is what you wanted to hear. But again, it's interesting because you can approach a various amount of problems. We only talked about simulating quantum systems or optimization problems in graph theory, but you can also look at financial optimization, Nash equilibria, or number factorization. You also have a set of tools of algorithms, a class of algorithms. We talked about its variational algorithms, but there's also many other types of algorithms designed for certain problems. So you can always mix and match between the problem and the algorithm you're using. And you can also continue your mix and match with your preferred error mitigation or error correction method. So again, we only really talked about 2 error mitigation methods, but there's also the stabilizer codes for those familiar with it. That's an error correction method. And what I work on, although I didn't really talk about it much today because it was sort of a general overview of how to go from theory to hardware, is how to make custom-made error mitigation techniques. Oftentimes, your problem has some sort of structure that you can be aware of, like a symmetry that you want to pose. And at the end of your circuit, if you sample a bit string that doesn't respect that symmetry condition, then you can throw it away. So to make these custom-made problems, you need to custom-made error mitigation techniques. You need to go back to the original problem. And if this did arise, I'm interested in you. I want to leave you with some food for thought, which is related to my current project. So if you're interested or have answered to any of these questions, really please email me. So the question for those of you that are familiar with game theory is how to encode the Nash equilibrium into the ground state of a Hamiltonian that you can also kind of efficiently implement on hardware. So Nash equilibria are a lot harder to describe than the kind of combinatorial optimization problems that we looked at today. So this first step is actually a lot harder than what you might think. And then step 2 in our recipe was what algorithm should I use to solve it best? And finally, what kind of error mitigation techniques can I use to make sure that my results are good? And with that, I thank you for your attention.